So we'll spend just a few minutes here in the beginning. We'll look at one partial fractions and one trig sub and see how it goes. We could do the same thing next class if people want. I want us to get comfortable with this. I did record my 10 o'clock class and I did things a little bit differently for the trig sub on Friday, and that's up on YouTube, so you might check it out. There were two different examples, different from the ones that we did together on Friday. All right, so either Dawn or Sam, can one of you guys give me an example? Can somebody give me the problem from the homework for 17? Did I get that right, Dawn? Okay, so we're going to try integrating this one. It's in the homework that's on partial fractions and trig sub, so it's a big clue that it's one of those things. The trig sub, the telltale sign for trig sub is like an x squared minus a squared or an x squared plus a squared. Nothing with x cubes in it. This is not a... Yeah, so we're going to factor the bottom. And it gave you the factor, so that's a nice thing. So we'll rewrite the integrand in factored form. So what are the factors, Ernie? Okay. So the telltale sign for this one is that the bottom is factored. And if the bottom is factored, then maybe partial fractions is something to try. So first thing we need to do is set it up correctly. So the setup for this one, I've got a linear term, x minus 5. Everybody understand when I say linear, x minus 5 versus the quadratic x squared plus 1? So if you have an x minus 5, what goes upstairs? Put an a up there. Linear terms get a single constant up on top. Plus, I'll put the other denominator, x squared plus 1. If it's quadratic and you cannot factor it, it gets a completely different looking thing. What does it get? Bx plus c. Done. Does it mean a squared? Yeah, I mean it could mean an a squared plus x squared. Are you thinking a trig substitution kind of thing? Right. No, this is a partial fractions because it's got the product of two different things. That's why it's going to be a partial fractions. If the bottom factors, try partial fractions. That's pretty much the biggest hint I can give you as to when to try partial fractions. Okay, so next thing we do is multiply both sides by the LCD. So let's do that. So I'm going to multiply this whole thing by x minus 5 and x squared plus 1, which means this thing is going to come in and hit the left-hand side and hit both fractions on the right-hand side. It distributes all the way through. Good things happen on the far left. What happens when I multiply the red LCD by the left-hand fraction? Cancels completely with the bottom, so what's left? Just the top, 10x plus 2 equals. Okay, now we're multiplying the LCD by this fraction right here. What cancels? The x minus 5s will cancel, so I'll be left with the a as well as the x squared plus 1. And the last multiplication is the LCD times this fraction. What cancels? X squared plus 1. What's left? X minus 5 times whatever was there before. So we go bx plus c, bring those parentheses in, times x minus 5. Okay, the goal for this whole problem has been to find a, b, and c. What's the technique at this point? Yeah, we're going to plug in values for x. And sometimes they're really nice values for x that you plug in. You try those first. What value of x makes this thing go away? X equals 5. So definitely x equals 5 is good. What value of x makes this thing go away? What's that? What makes that one go away? Oh yeah. So just separately, what value of x makes this? Nothing. Nothing makes that go away. So this one isn't going to be as nice as the other ones, where you can just, yeah, an imaginary number will make it go away. We're not plugging that in. So we're going to plug in x equals 5. It's the only real nice number to plug in. And then we'll plug in different numbers. They won't be as nice, but that's okay. So all of the x's become 5s. So on the left-hand side, 52 equals, on the right-hand side, how many a's? 26 a's. Plus, that x over there is also 5. So this is going to get kind of messy here. We've got 5b's plus c, but then something very good happens, times 0. So this whole thing right here is nothing, and 26a is 52, and lo and behold, a is a nice number. It's 2. If you came in late, this is number 17 from the homework. Okay, we found A. Now we got to try to find B and C. Okay, this isn't going to be as nice as the other problems that we've done, but what value of x makes this B term go to 0? 0. So that seems like a good number for x to plug in. Plug in x equals 0 and the B term drops out. The C term will still be there. That's good. I want to find what the C term is. The A term will also still be there, which isn't so great, but I know what A is now. So it's not that big a deal. So let's plug in x equals 0. On the left-hand side, x is 0, so we get 2. Equals, we just figured out that A is 2, so 26 times 2, I'll just write that out, plus, and we said that when we plug in here, no, not there, here, the x is 0, so the B term goes away. So what's in the parentheses? Did I make a mistake? What did I do wrong? I'm plugging 0 for x. Oh, I used the red equation. Thank you, thank you. Okay, should have plugged in x equals 0 there. So how many a's do we have? 1. Thank you. So we get 1 times a. I'll just write it as 1a, and then we'll replace. Okay, and then plugging 0 for this x, that term disappears. We just get c times, and then 0 for this x gives us -5. Everybody see where that equation comes from? 0 is for all the x's. The goal is to find c, but a is there, so we're going to replace a with the 2 that we found up above. We found out that a was 2. Subtract 2 from both sides, and divide by -5. Turns out c is 0. Any questions on finding c? What do we still have to find? Still need b. Okay, at this stage, I don't think there's a nice number we can plug in that will get rid of really any terms up here. But the fact is, this equation here in blue is true for every single value of x. So you can plug in any value of x that you want. X equals 17, if that strikes your fancy. How about we try x equals 1? But really, any number at all is fine in any in that blue equation. So let's just pick x equals 1 and see what happens. X equals 1. How much is the left-hand side? 12 equals. And I'll say, you know, like, so I've given tests and quizzes on partial fractions before. I think the most common mistake is to forget that you plug x equals whatever into the left-hand side. I think everybody plugs in the right x over here because they're doing it to try to make something disappear. But a lot of times people forget, and instead of putting x equals 1, they'll just copy the left-hand side, 10x plus 2 equals, and then they'll plug in x equals 1 on the right-hand side, and they'll be stuck because you'll have b's in the equation, and you've also got x. Every x in this equation becomes 1. So left-hand side is 12 equals how many a's when x is 1? That's 2 a's. Plus, in the parentheses, the first parentheses here, what do we have when x is 1? B plus c. And then in the last parentheses, when x is 1, negative 4. Everybody see where the purple equation comes from? Okay, the goal is to find C. The goal is to find B. We're going to use the values that we found for A and C already. So this becomes 12 equals, how much was A? A was 2, so this is 4, plus B plus, how much is C? 0, we found that. And now all of a sudden, one equation with one unknown. I get B is negative 2. Okay, so we haven't done any calculus yet, so it's probably time to do some of that. What are we going to do? We have the original integral. It's way up here. We factored the bottom, or they gave us the factorization. And now I think we're ready to plug into that thing with the purple stuff in the numerators. We just found A, B, and C. So I'm going to come up here and write equals integral of. So I'm going to circle this part right here. This is what I'm plugging in up there. We found A. How much is it? A is 2. So this becomes 2 over x minus 5 plus. We found B. It's how much? It's negative 4. Is that or negative 2? Negative 2? Somebody remind me. Negative 2. Thank you. So that's a negative 2x. But now I'm looking at this thing here. Plus C. How much was C? 0. So that thing in black, that's the entire integral. Okay, and then we're going to stop this one here, but we'll just give one brief hint for each of these integrals. What's the technique for this one? It's a u substitution. And what are we going to let u equal? X minus 5. That's a good idea. What's the technique over here? Another u substitution. What are we going to let u equal? X squared plus 1. That's it. Then you do the calculus part. The calculus is way easier than the non-calculus. Any questions on that? Piece of cake. Yeah, it's just a lot of steps. I think once you practice, the steps aren't hard. Once you've got some practice. But you got to practice. Get to the point where you have a clear sense of, okay, what am I doing now and how am I going to get to the next step so that each part is kind of motivated by what you're after. Sure. Is that a trig sub? What is it? x squared this. Okay. Okay, so my first reaction to this one, and I'll say this, I think that sharing my first reaction is important because integrals are way harder than derivatives. And really the only thing that I bring to the table that some of you guys don't yet have is the experience with the integrals. You know the techniques that I know. I'm not doing anything fancy. It's really just what are your first impressions when you see a brand new integral? So I'll try to kind of vocalize what my first thoughts are about this one. So the first thing I think is maybe a u substitution where u is equal to the denominator. If I see a complicated denominator, oftentimes the first thing I'll try is just letting u equal that thing. What's the derivative of the bottom? 2x plus 4x cubed. Does that look like the top? Not even close. So that's the first attempt. It didn't work. We move on. But the nice thing is that with some practice and experience, that failure takes like 5 seconds. So it's not that big a deal. My next thought was to maybe split it up into two different integrals. If I see a few terms upstairs, sometimes I think, okay, maybe splitting it up will help me. If I see Ernie gave me a look, he said the look basically said that's worse. And I think that's about right. Is this first integral anything that we can handle? Doesn't seem like it. And the second one also doesn't seem like it. But anyway, it's something to try. If you have multiple terms upstairs, just think for a moment, what if I split it up? Could I handle each of the little pieces? In this case, that doesn't seem to work. My next reaction is that the bottom factors, and if the bottom factors, I think partial fractions. If the bottom factors, I think partial fractions. So that's my thought process for this one. And then I would factor the bottom. X squared comes out. 1 plus x squared is in. Now, as far as seeing through the problem, this is as far as my mind goes. I can't look at that and say, oh yeah, I see exactly how it's going to work out. Everything will be fine. But at this point, I would definitely try partial fractions. And if that didn't work, I'd be in a whole lot of trouble. Did anybody get this one? Does partial fractions work? So then let's just write down the setup because we really didn't do very much where we had repeated factors in the bottom. So let's just do the setup and then we'll do the new stuff for today. Okay, I'm gonna write the last one first. 1 plus x squared goes here. And the first part is an x squared. So the question is, how do we handle x squared when it comes to setting up this partial fraction thing? It's two separate ones. Yeah, x squared is a repeated x. It's a repeated linear thing. So when you have a repeated linear thing, you write the first one, and then you write the same thing but squared, and if it were to the third power, I'd have one more term cubed. Whenever it's a repeated factor, you got to build your way up to it, starting with the first power and ending with whatever is in the problem. And then what goes upstairs on top of the x? That's a single a, because that's a linear thing, the x. What goes on top of x squared? It's a b, it's not a bx plus c, which is strange because it's an x squared. And right over here, for this 1 plus x squared, what are we going to put upstairs? We're going to put a cx plus d, which is really weird because we just said, it seems like the two things don't match up, but they're different. I'm going to put parentheses. X is a linear term. It happens that it was repeated, but still, any linear term you have, you put a single letter upstairs. But if you have an irreducible quadratic, that is a quadratic that you cannot factor, that's where the linear things come in. I can factor x squared perfectly well. It's x times x. I cannot break down 1 plus x squared anymore. So that's the difference between the two. So I'm happy to do the rest of this problem after class, but I want to move on to the new stuff. But I think the setup is a real big part of this problem. Any questions on that one so far? Okay, so how about we say this? What are we doing? So on Wednesday, maybe for the first few minutes, we can do a trig sub from this homework. Whichever one you guys want to do is fine. I want us to get comfortable with it, but I perfectly understand that these two techniques are quite challenging. They're both tough. What's that? This one ends up as a trig sub? You do. Let me say you can avoid doing a trig sub in this problem. I'm just going to make up this one. I'll say it turned into a 2x minus 3, which I'm certain it doesn't, but let's just make something up so we can handle it. That integral right there we can do without a trig sub. It's fine to do a trig sub. You see 1 plus x squared, you think trig sub? Sure. But I see two terms upstairs. And when I see two terms, what can I do? I can split it up. 2x over, and then minus 3 over. And those are two integrals that we can handle without any fancy techniques. This one first, it was on the take-home quiz with arctan. Right? It's arctan. Arctan x, right. And then this one here, this is a u sub. If you have a complicated denominator, first thing to try is letting u equal that denominator. What's the derivative? 2x, perfect, it's upstairs. Now I just made it up, it's probably not 2. So what if it were 5? Can you handle it? The derivative is 2x. You have 5x. Is that okay? Yeah. Just going to multiply by some constant. So it doesn't matter what the cx plus d turns into. You can split it up and have a u sub and an arctan. Okay. So let's start the new material, which is here on page 8. And while we're opening to page 8, just a couple of quick announcements. First of all, the scholarship deadline for the GCC Foundation scholarships is approaching. It is March 11th. This was the long list of scholarships that everybody in this room is eligible for. Some of them, I'd encourage you to throw your name in the hat. March 11th is the deadline. It's a relatively painless application process. Next thing is the calendar. So today we talk about approximating definite integrals. Also today your grading choice is due, so I'm going to pass this thing around. It's got the particular percentages down here at the bottom, so find your name, circle your option. There you go. And what else is happening? On Wednesday, I will hand out project number 4, and on Friday we have our third quiz. Questions on the calendar? Yes. Anybody else wasn't here last time? Okay. Here's the new calendar. Okay, so here on page 8, we're going to go to number 1, and can we start with, let's see who's ready. Andrew?
There are other shapes that we can use that will give us even better approximations.
Thank you. Okay, here at number 2, new notation. We're going to let left of n and right of n denote the Riemann sums using n left and right rectangles respectively. So let's see that notation work on the next page. I've got the integral from 1 to 3 of 3x squared dx. Why is it very silly to do this one using rectangles? Because we know how to do this one. Okay, well, let's just go ahead and get the right answer right now. What's the antiderivative of 3x squared? It's just x cubed, yes? Good notation. Notice all the equal signs in my example up here. Use lots of equal signs. Plug in 3, plug in 1, and subtract. I got 26. Is that right? Any questions on that? All right, so that's not a big deal, but let's pretend we didn't know what the answer was, because for just about any integral you make up, you're not going to know what the answer is, because just about any function is not integrable. No matter how many crazy techniques we come up with, including partial fractions and trig subs, most functions do not have a simple antiderivative. So let's do this. We're going to find left of 2. The 2 tells you how many rectangles you're going to be drawing. You're going to be drawing 2 rectangles. We're still going from 1 to 3, so I'm going to go ahead and draw some vertical lines here to indicate we're going between 1 and 3. If we're using 2 rectangles, that means we cut this space into 2 equal pieces. So where's the dividing line? Right there at 2. All right, that works out pretty well. And these are going to be left rectangles. So in this first interval, 1 to 2, you pick the left-hand endpoint. Which number do you pick? You pick 1. And you take the number 1, go up to the curve. That determines the height of the rectangle. You draw to the right until you're directly above the dividing line there, and you go back down. That's the first rectangle. Go ahead and draw the second left rectangle. Okay, so we've got 2 left rectangles, and we're going to find the area of each of these rectangles. So we need the length of the base, and we also need the height. How much is the base for each? Is 1. The height is harder. Now, they're tiny numbers, so if your eyes are really good, you might be able to estimate the height. Can somebody just ballpark the height of the first rectangle? 2.5, 3. Okay, so if you only have the picture to rely on, then the best you can do is estimate. But we have more than that. We have what that function is. What is it? It's 3x squared. So let's use that. You want to find f of 1, because that's where the height of the rectangle is. It is 3. You also want to find f of 2. That's the height of that rectangle. Tiffany, did I make a mistake? I did. I don't know what I plugged in. I did 2 times 3 squared for some reason. Should be 3 times 2 squared. Okay, so we got 3 and 12 are the 2 heights. So then we can find the areas of the rectangles. The area is the base times the height. First base is 1, first height is 3. Second base is 1, second height is 12. So 15 is the area, the sum of the areas of the tube. Questions on that? Base times height plus base times height. You can add f of 1 and f of 2 in this case, but it's only because the bases happen to be perfectly 1. Okay, is that a good estimate for the right answer, which is at the top here? Not really. The right answer is 26. The area should have been 26. We only got 15. We're barely at half of what the right answer was. How come? We should have gotten all of this space in here. We missed it completely. We also missed this space in here. Turns out that was pretty significant. What was the area of those two curvy triangles? It's 11. So all the stuff we missed. So that's not very good. So how could you do better with left rectangles? More of them, right? Using 2 of them was very rough. Use 20, use 200. You don't want to do it by hand, but technology can do it no problem. Okay, right rectangles, it's the same idea. I'm going to skip it unless people really want to see it. Just a matter of drawing 2 different rectangles, but this time have them go to the right-hand side of each interval. And now we're going to go down to 4, and we'll go to Richard. Okay, so we're going to fill in this blank here. Anybody remember the formula for the area of a trapezoid? There's a height, there's 2 bases. I'm going to put that over there. Good. That's the formula for the area of a trapezoid. Thank you, Cole. It was about to get awkward in here. So it's half the height times the sum of the bases. That's right. And actually, I really like what Cole said, where he said it's actually the average of the 2 bases. That's a really nice way to think of it. Base 1 plus base 2 divide by 2. That's the average length of the 2 bases. And then you multiply that by the height. Super. Okay, so we're going to draw 2 trapezoids because, again, the thing in the parentheses is 2. So we come down here. It's the same, our favorite interval from 1 to 3, which means we're cutting it into 2 pieces. So right there in the middle in this case. And then we're going to draw 2 different trapezoids. So let's draw the first one. Between 1 and 2, which height do you use? Like up above, we use the left-hand endpoint to determine the height. We're using both. You go all the way up to the function at 1. Separately, you go all the way up to the function at 2. And then where's the trapezoid? You connected 2 dots. So just draw a straight line, connecting the 2 dots. Now I've drawn my line a little bit exaggerated because the line is so close to the curve, but I just want to highlight the line is it below or above. It's going to be just a tiny bit above, just a little bit above the curve. And then separate trapezoid between 2 and 3. So draw both heights and then connect the dots. And again, I'm exaggerating mine, but if you have a straight edge, that'll be a little more accurate. And then we're going to use this formula in blue, find the area of each trapezoid, add them up. Go ahead and do that with your neighbors. Okay, so one group says the area with the trapezoids is 27. Anybody else get that? Yeah. Anybody get something other than 27? Any questions on the trapezoid? Yeah, Bubba. We're going to do something different on the last picture. Yeah.
Trapezoids going the other way?
Nope. I don't know what the other way would look like. Oh, like rotated? Let's see. Okay, so a couple of folks actually made a nice observation that the trapezoids has an awful lot to do with the left and right rectangle approximations. So I know we skipped the right rectangle one, but I did it while you guys were doing trapezoids. I got 39 was the area using right rectangles. Is that too big or too small compared to the right answer at the top? Way too big. It should be 26. We got 39 because the red rectangles here grab a lot of stuff that's outside of the area. But I think I heard this table here. What did you guys say about the trapezoid?
Same as the average block.
Yeah. If you take a look at the left answer, which we did together, was 15. And the right answer, which I did, was 39. And you average 15 and 39, you will get exactly 27, which is pretty cool. And it turns out to be true. So here it is. I think we're up to Maggie for number 5. Okay, so here's our formula. It just says average the left and the right. So how much was the left up above? It was 15 plus the right one I did, and I got 37, 39, thank you. And we divide that by 2, and we get the same 27 that we got doing trapezoids, right? So if you know the left and the right, just average them. That gives you the trapezoid answer.
Trapezoid on the left is like the same values as the left of 2. The trapezoid on the right is the same.
That's right. Good. Okay, which of the 3, left, right, and trap, was the best at estimating the right answer, which was 26? Trapezoid. It was pretty close. You got 27 instead of 26, and we only used 2 trapezoids. If we used 10, we'd be quite accurate. Maggie. Hmm? Try adding them together again. I think it should be 7.5. Yeah. Yeah. Okay. All right, number 7, we're up here to Ashley.
Right, mid, and use 10 draw 2 midpoint rectangles, right, right, and find mid 2, which are 4 up.
Okay, so the blank picture, we're going to draw midpoint rectangles. So still, we've got our interval 1 to 3, and we're still cutting into 2 rectangles. So you still cut it right there in the middle. But now to determine the height of the rectangle, you don't go to the, so here we're between 1 and 2 right now. You don't go to the left point at 1. You don't go to the right point at 2. Where do you go? You go to the midpoint. So we're going to go to the midpoint, which is right here. What number is the midpoint? It is 1.5. You're going to go up to the curve. That's the height of your rectangle. To draw the rest of the rectangle, you need to go left and right from that point, and then straight down. Okay? You go to the midpoint, and then you go left and right. So go ahead and draw the second midpoint rectangle in that same picture. If you're stuck on how to draw it, ask a neighbor. And once you've got both drawn, go ahead and find the areas of the 2 rectangles. Okay, so we draw the 2 midpoint rectangles, which means you got to figure out where the midpoints are. In this case, 1.5 and 2.5. You plug them both into the same function, 3x squared. And then we just add our 2 areas together. So the area of the first rectangle, the base is still how long? Still 1, right? The 1.5 doesn't make any difference. The base is still 1 times the first height is 6.75. Plus the second base is also 1, and the second height is this 18.75. So is that 25.5? Is that right? Yep. Okay, which of the 4 was the best? The correct answer was 26. So the midpoint one was the best. You see how we built from worst to best? Isn't that exciting? Yeah, and there's no guarantee that it's always going to be like this, but there is something quite nice about drawing midpoint rectangles. What's good about drawing a single midpoint rectangle? Right, don't we have, like when we did the left rectangles, first, both of these left rectangles were what, over or under estimates? They were both under. They were consistently under, and the first under and the second under just added together to give you more and more error. How about both right rectangles? They were both over. How about both trapezoids? They were both over, not by a lot, but they were both over. But when you draw a single midpoint rectangle, you accidentally capture some stuff that you don't want, but you also miss some stuff that you do want. And, you know, gosh, those 2 shapes are very close in terms of their areas. And so they almost cancel each other out. And with just 2 little rectangles, we've got a pretty good approximation for the right answer for this one. Okay, next page. Which ones, the midpoint ones? Yeah. Well, I mean, the idea here is that really anything that you do, as long as you do enough of them, you're going to be fine. like practically speaking, your calculator is doing something more complicated even than the midpoint ones, and it gets even more accuracy. All right, so let's take a quick look at this sketchpad thing. It is here. So here's a function. This function is the 3x squared function that we were starting at before. So it's the same function we saw before. We want the integral from 1 to 3, so it's this red interval down here. All right, the correct answer is that. How come it's not exactly 26? Some of them can now, actually. Yeah, these are just estimates here. I couldn't get any closer. This is just a dragging thing, and I couldn't get any closer than that to 1. So it's very close to 26. All right, 2 left rectangles are there, both of them under. We got 15, very close. Let's take a look at the 2 right rectangles, both of them over. We got 39 for that one. Then we have the trapezoids. And you can see, I mean, you have to have real good eyes, but can you guys see? It's just a tiny bit over the curve. And again, just a tiny bit over the curve. So very good accuracy there with just 2 of them. And then finally the midpoint ones, you can see the line right there, right at the midpoint. That determines the height of the rectangle. And that, in this case, we got 25.5, I think, was our answer. Okay. What's that? I prefer GeoGebra, but I already had this thing done in Sketchpad, and I didn't want to start over and make a new one in GeoGebra. And then the other nice thing about this, let's hide those guys, and let's just bring the left rectangles back, is that there's a button here that we click, and we just get more and more of the shapes. And so with n equals 10 left rectangles, it's 23. Remember, the right answer was 26. And you can see how close we're getting here with the midpoint and the trapezoid one. And you can use more and more and more, and the picture doesn't mean anything, but all of a sudden these numbers are really honing in on the right answer. Okay, let's come back here. Number 9. For some functions, we can easily tell if our approximations will be over or under estimates. If f is increasing, for example, like the picture we've been looking at all day, which of these 2 estimates was consistently under the right answer? Was the left. And which one was consistently over? Was the right. So let's fill those things in here. If f is increasing, left is under, right is over. If f is decreasing, we're just going to swap them. So draw a quick picture either by hand or in your mind. Convince yourself if f is decreasing, I just swap. But right-hand estimates are always under. Okay. The trapezoids that we drew, were they under or over? The trapezoids were over. Is that because the thing was increasing? So here's a picture that we had, and we drew some trapezoids. I'll just draw a very big one. And it's easy to see the trapezoid is going to be over in that case. Is it because the function is increasing? All right, I'm going to draw another trapezoid for this kind of increasing function. So again, a very crude trapezoid. And now what kind of a trapezoid is that? That's under. So because the thing is increasing or decreasing has nothing to do with whether the trapezoid is under or over. What's the deciding factor here? It's the concavity. So in the first picture, the function is concave up, and the trapezoid is what? Too big or too small? Trapezoid is too big. So we're going to fill that in. If the function is concave up, then the trapezoid is too big. If the function is concave down, the trapezoid is going to be too small. Now I feel like there's only one other kind of shape we've used, and there's one blank left. So by process of elimination, what are we going to put in there? Is the midpoint. But let's see if we can convince ourselves that it's true, not just because it's the only thing left to put in the blanks. So let's go ahead and draw something concave up. And I'm going to draw a midpoint rectangle. So there, that's not what I meant to draw. So we go to the midpoint, we go up to the curve, and then we go left and right. And then straight down. So the question is, which shape is bigger? Is it the extra space that you didn't mean to get, or is it the space that you missed? It feels like looking at this, the space that we missed is the one that's bigger. We buy that? So if the space that we missed is bigger, then does the midpoint over or underestimate the right answer? It underestimates it. We grabbed some stuff we didn't want to, but we missed even more. We didn't grab enough. So in a concave up function, the midpoint rule underestimates. Yeah, it could be equal, but it's less than or equal to. And the same kind of picture for something concave down. You can draw one later if you want to. Midpoint will overestimate anything that's concave down. All right, number 10 is a very good quiz question. Say that again, number 10 is a very good quiz question. What we're trying to do is take this integral, the integral from 1 to e of ln of x, and we're going to order 5 different things. We're going to order the 4 estimates and then the actual right answer, the actual integral. Okay, so I'm just going to get my shell up here. Let's see, it says from smallest to largest. So I'm just going to put a bunch of less than or equal to signs here, 4 of them. We're going to put 1, 2, 3, 4, and we're going to put the original one will go in there somewhere too. Yeah, so which one is going to be in the middle? The right answer, right? Like the actual integral itself is going to be in the middle, and the estimates will fall on either side. So that one's easy. We'll just put it right in here. 1 to e ln of x dx. Yeah, I think that's another good assumption. What do you guys think? Left and right always do worse than trapezoids and midpoints. So it's really just a matter, like we know that in some order, the left and the right will be out there, and in some order, the trap and the mid will be in here. So it's really just a matter of putting the pieces into their slots, okay? So in order to figure out left and right, are we interested in the concavity or in the increasing, decreasing? For left or right? Increasing, decreasing. What's the function that we're imagining in this case? It's ln of x. It's the function we're integrating. That's the function that we're after. So a very quick sketch of ln of x. As soon as you know whether it's increasing, decreasing, concave up, concave down, you got everything. So draw a quick sketch without the calculator, ln of x. So it starts almost at the y-axis and then grows very slowly. Is it increasing or decreasing? Increasing. Now, it's increasing all the time, but if it were something that changed, where's the only space that we care about for this problem? Is between 1 and e. That's all that we care about. So between 1 and e, 1 happens to be that number right there. E is out here someplace. That's all that we care about. It doesn't make any difference in this one because it's always increasing. Yeah, because ln of 1 is 0. Okay, so the function is increasing in that interval. So what goes in the first yellow? Is it left or right? We got it written up above. If the function's increasing, the left ones are too small and the right ones are too big. So let's fill those two in. So this is left of n. And I put the n there to say it doesn't matter whether you're doing 2 rectangles or 2,000 rectangles. Still, they're going to be underestimates. And right rectangles will be crude overestimates. Okay, so far so good. The other aspect of the curve that we need to know about is concavity. This curve is concave down. Okay, so for concave down, which one is always too small? Is it trap or mid? Okay, so we'll put trapezoid over here. It's too small. And that must mean that the mid is too big. Any questions on that? You think that's a good quiz question, don't you?
Yes.
Yeah. Okay, let's move on to 11. Tiffany. Okay, so if we use parabolas, then we might think, okay, they could be better because we've been doing straight things instead of curvy things. Parabolas are curvy. So here's the formula. The Simpsons Rule of N, meaning like instead of two rectangles, do two parabolas, is 2 times the midpoint approximation plus the trapezoid approximation divided by 3. In some sense, it's a weighted average of the two things that we did. You take double the midpoint, so it's like 2 midpoints, and a single trapezoid, that's 3 things altogether. You divide by 3. So let's see if we can get the answer for the one we did on the previous page. So if we wanted to do Simpsons rule with 2 parabolas, we use our formula. So we take 2 times the midpoint. What was our midpoint estimate? 25.5. Plus a single one of the trapezoid estimates, which was 27. And then we divide by 3. Anybody have it? 20, 26. Woohoo! Okay, it's not always perfect, but I think generally it's better than any of the 4 that we've done. Did we make a mistake? I was expecting it to be perfect.
Oh, wait,
Yeah. Okay, so it's not always perfect. In fact, the reason it's perfect here is what's the thing we're trying to approximate in this function, in this formula? Was a parabola. 3x squared is a parabola. If you estimate a parabola with 2 parabolas, it's going to be perfect. But I guess I will say that almost all the time, this method is better than the left and the right and the midpoint and the trapezoids. And it's not too hard to do. Get the midpoint, get the trapezoid, do this weighted average, and you've got Simpsons rule. It's not at all clear that it's using a parabola. Here's the key phrase. It is not intuitive that this formula has anything to do with parabolas. There might be the derivation of this formula in the book, or not that formula per se, but like a different version of things. I don't remember the exact formula for, this isn't the traditional way to write it, but I don't know what it's messy and I'm not going to write it down, but you might see some long sums in your textbook for Simpsons rule, and it's got like all these different coefficients, like a 2, a 4, a 2, a 4, alternating. I don't remember. But it might go through the derivation in your book of actually drawing a few parabolas and then figuring out what the coefficients are of those parabolas. But we're just going to use this guy. Okay, 13, Steve. Right. So your parabola, when you use that FNINT function, it's not doing rectangles, it's not doing trapezoids, it's doing something like parabolas, but a little bit more complicated. But it's very accurate, which is why when we type it in, we just accept that this answer is good enough. It's to 8 decimal places already. No, the 83s, 84s can't do antiderivatives. Some of the higher ones can now, but those ones are not doing. It doesn't even know that 3x squared came from x cubed. It's only approximating. Which actually kind of makes sense because sometimes, like instead of getting the right answer, 26, you'll get something like that, right? Because it's estimating. All right, number, let's see, 14, we're gonna skip. We're going to do 15 in a moment, but let me show you just one more set of pictures here. Suppose that instead of looking at area under curves, which is what we've been doing for a few weeks in this class, we went to Calc 3. And things in Calc 3, well, what's another name for Calc 3? Anybody know? Multivariable calculus, multivariate calculus, which means multiple variables. Instead of just f of x, one input, x, you might have f of x and y, which means we need a third dimensional thing to graph it. So instead of curves, which are one-dimensional things, what's the two-dimensional analog? What is it? So curve has an area, but yeah, we're going to have volumes of things. So we might have planes, or maybe a little bit curvier surfaces. Just imagine some kind of a surface thing floating around above the floor, and then instead of finding the area under the curve, we have the volume under the surface. Fair enough. Instead of using rectangles to estimate area, what's the three-dimensional analog of a rectangle? Like a rectangular prism, something that looks like a shoebox. Could you imagine you have this wavy surface up here, and underneath the surface you just draw a bunch of shoeboxes that have the height that gets you up to the surface. And so you, well, our calculator can't do anything multivariate. I don't know what the fancier ones are doing now. Good question. So let's take a look at some pretty pictures here. All right, so we can take a look at this guy. The function, it's real tiny, but f of xy equals x squared plus y squared is a surface, and it just looks like a bowl. So just imagine like a soup bowl or something like that. That's what that curve looks like. That's what the surface looks like. And so you can see here, you can almost see the surface just looking at these shoeboxes, right? It kind of looks bowl-shaped. How could you get a better approximation? More shoeboxes. So right now we have 10 in each direction, 10 in the x, 10 in the y. I'm going to ramp this up to 40 in the y. So you can see it looking more bowl-shaped, but you can also see that they're not shoeboxes in the traditional sense anymore, right? The shoebox normally is a square on the one side, or maybe it's not, but this is definitely not. And we can ramp it up and have 40 there, and so now it really looks like the actual surface that it's representing. The right answer is 42.66 repeating. That's the true volume using, what is this, 40 and 40. So that's 1,600 shoeboxes down there. We got 42.64. So off by about 3/100ths using all those shoeboxes. The other thing is the shoeboxes that we've drawn here are actually midpoint shoeboxes. You have to decide. You got this square in the floor, and up above the square is the surface, but the surface is changing height even above one little square. So you have to decide which height do you want to pick. You could always pick the one that's the lowest. You could pick the highest. You could pick the one in the southwest corner, right? You could pick a lot of different ones. So this dot right here tells you which point you're picking inside of the square in the floor to determine the height of that shoebox. So if I decided to pick the northwest corner of each of these squares, then you can see things have shifted a little bit, right? We don't have the kind of symmetry that we had before. And you can move stuff around. I think it's pretty cool that you can just like grab this and move it around and everything shifts around. So that, what's that? So here the shifts are not as dramatic because the difference between the height in the northwest corner and the height in the southeast corner is not that different because the boxes are really tiny in the floor now. Okay, so there is that. We can look at some other surfaces. Sine of x squared plus y squared. There it is. Let's see, 2.971, 2.967, so not too far apart. We can look at cosine of x squared minus y squared. There. Yeah. Yeah, something to look forward to. And then this guy, x squared minus y squared is, yeah, we'll do stuff by hand next semester. Yeah, it's a Pringle. All right, let's see if we can at least get started on number 15 here. Okay, we'll go to Dawn for 15. Okay, so there's the pool, weird shaped pool. So whoever was rich enough to afford the pool has hired us. They have enough money to hire us to tell this person what the area of the pool is. It's important for them to know. So how many different spaces do you see in the pool? I heard 8, I heard 9. I heard another 8. How many spaces in the pool? There are 8 spaces in this pool. Yes? 1, 2, 3, 4, 5, 6, 7, 8. 8 spaces. So we could estimate this thing using how many rectangles? 8 rectangles, no problem. You could use 8 midpoint rectangles, 8 left rectangles, 8 trapezoids, but things are weird because it's all curvy. Strange. So let's just look at the rectangles to start. Suppose that we wanted to do right rectangles. That is to say, we're always going to pick the right-hand number in the picture for the height of the rectangle. So first, how much is the width of each of these rectangles? Each of them is a 2. All right, so that's easy. The width is 2 for all of them. So let's look at the first rectangle on the far left. We're going to use the right-hand point. So between this point and this point, we pick the right-hand one to determine the height. What's the height of that rectangle? Is 6.2. So I'm imagining this rectangle going out there, going down there. 6.2, it'll be too big, obviously. Let's skip ahead to the end game. Let's look at the last rectangle. We're using the right-hand point between there and there. What's the height of that? It's 0. The height of this last rectangle, if I pick the right-hand number, my choices are either 4.8, that's the left hand, or I don't go up and down at all. So the height of that last rectangle is 0. So the height over here is 0. Okay? And so in my mind now, I'm going to translate these things right here to points. Let's try it this way. So 2, 4, 6, 8. What's the last number in this list? 12, 14. Is that it? Does it go to 16? I need 8 spaces. That's 7. We've got one more. 16. Right? 8 by 2, 16 meters long. And now I'm going to start plotting some points. And each point is going to represent the width at the particular spot in the pool. So for example, 2 meters into the pool from the far left, what's the width of this pool? 6.2. So 2 meters in, I'm up here at 6.2. At 4 meters in, 7.2, right up there. 4, 7.2. How about 16 meters in? That's the 0. So this last dot right here is at 16, 0. Where's the first dot? I didn't draw the far left dot. Where should I put it? We should also put it at 0. 0 meters in, the width is 0. So you don't need to plot all of the points, but I'm just plotting a few of them so we understand that it doesn't make any difference that this shape is kind of strange. Just in our minds immediately, we're just translating it into a normal, it's on the x-axis and each point has a height. Doesn't make any difference that it looks like a kidney bean. It's fine, right? This is just an ordinary function. And so you can do all of the things that we did earlier today using those numbers. So first thing next time, maybe you guys can finish this one and we'll just get an estimate to make sure everybody's estimating okay. And then we can start with a trig substitution and then we'll jump into the new material, okay? All right, have a wonderful Monday.